Welcome to More Learn, More Teach, where I attempt to simplify the complex. Today we're going to talk about significant figures. I have on the board a 9 significant figure number, 1, 2, 3, 4.5, 6, 7, 8, 9. There are 9 significant figures in this number here, which would indicate that I have measured something to 9 significant figures. This is important because I want to understand when I multiply, divide, add, subtract, the number I end up with, I don't want it to appear more or less accurate than the numbers that I start with. So this number, 1, 2, 3, 4.5, 6, 7, 8, 9, could be expressed as 1, 2, 3, 4, 5, 6.789 if I multiply this number by 10 to the 2. So you see, if I take this number, multiply it by 100, I end up with this number. Okay, so it's just expressing the exact same number, but in a different term. Talk more about why you want to do that in a minute. I could also say this number is 1, 2.3456789 times 10 to the minus 2. If I took this number and divided it by 100, or multiplied it by 10 to the minus 2, or multiplied it by 0.01, I would get this number right here. So again, these are all three the same numbers, right? These are all three the same numbers, different ways of expressing the same number. And in each case, I have all 9 of my significant figures. All right, continuing on with our significant figure discussion, let's do a quick review. 10 times 10 is exactly the same as 10 to the first power multiplied by 10 to the first power, which, if you multiply these, property of exponents, I end up with 10 to the 1 plus 1, or 10 to the 2, right? So this shows you how 10 times 10 is 100, which is equal to 10 to the 2. If I divide 10 by 10, that's exactly the same as 10 to the 1 divided by 10 to the 1, which is the same as multiplying 10 to the 1 times 10 to the minus 1, which allows me to add these exponents. I could have just said 10 to the 1 minus 1. I could have used the divisor rule for exponents, but I chose to use the multiplication rule. So 1 minus 1, or 10 to the 0, which is 1. So 10 divided by 10 is 1. 10 to the 0 is 1. Let's talk about some standard prefixes. So I've written on the board here a roughly log scale. It's not 2 scale, but it's a way of I have here a set of standard prefixes. It is easier for us to understand numbers if we group them in what's called orders of magnitude. An order of magnitude is a factor of 10. As we talked about over here, 10 times 10 would be 10 to the 2. So 10 to the 2 would be 2 orders of magnitude bigger than 10 to the 0. It would be 1 order of magnitude bigger than 10 to the 1, right? So 100 is 1 order of magnitude bigger than 10. It's 2 orders of magnitude bigger than 1. So I have here a list in orders of magnitude. It's not exactly per scale, but it's roughly a log scale. Starting at 1, so 10 to the 0 is 1. This will not have a prefix. So this would be like meters or grams, that kind of thing. If I go smaller than 1, I go through 10th, 100th, 1000th, millionth, billionth, trillionth, quadrillionth, and quintillionth. I could also say deci, centi, milli, micro, nano, pico, femto, atto. Going bigger than 1, I might have 10, 100,000, million, billion, trillion, quadrillion, quintillion. On this side, I would have deca, hecto, kilo, mega, giga, tera, peta, exa. There are more, but this is a good enough list for our examples. If I applied this, here's some examples. 1 millimeter, so milli, right? Milli is 10 to the minus 3. So a millimeter would be 10 to the minus 3 meters. A hectare, right? So a hectare would be 100, right? So hecto means 10 to the 2. So 1 hectare would be 100 airs. It's a unit of area. 1 microliter, right? So micro is 10 to the minus 6. So 1 microliter is 10 to the minus 6 liters. $1 billion, right? So billion is 10 to the 9. $1 billion is 10 to the $9. Let's have a note about zeros. So zeros can either be a placeholder or significant. It really depends. So if I look here at this number, I have 1, 0, 0, 0, 0, 0, 0, 0. These zeros are just placeholders. If these zeros were not in place, then this number would just be 1, which is not what we're looking for, because I want to represent that it has 7 orders of magnitude. So that's how I have these zeros. These are placeholders to put this here. So in scientific notation, I would represent this by the number of significant figures, which is 1. There's only 1 digit in this whole expression that is significant. It's 1. There are 7 placeholder zeros, so 10 to the 7. So 1 times 10 to the 7, this would be the scientific notation. If I stuck a 1 on the end, now I have implied that I've measured all the way down to that digit. So now all of these are significant because they all came out of the measuring device, every single one of them. They weren't just implied by the scale of the measuring tool. So here I have 1, 0, 0, 0, 0, 0, 0, 0, 1. All of those are significant, so they all have to come across when I'm expressing scientific notation. So all of my significant figures. Then I have to still account for the places, so that becomes 10 to the 8, because this digit is 10 to the 8 from here. Okay. So let's look at an example on the other side of 0. Same principle. See that if this was a decimal here, everything on this side is a placeholder to put the 1 such that it is 7 orders of magnitude away from the decimal. Well, here I'm going 4 away from the decimal. The only reason these zeros exist is to give me a placeholder. There's only 1 significant figure. Therefore, I can express this in scientific notation as 1 times 10 to the minus 4. 10 to the minus 4 because it's 4 orders of magnitude away from the decimal. Okay, again, if I put some extra digits on the end, now I've implied that the scale is better and I have actually measured this number, and these zeros are now significant because now they're no longer just placeholders. They are measured numbers. Okay, so now they're all significant and they all would have to carry over to my scientific notation. Okay, scientific notation, we only have the ones digit here, so we still have to go times 10 to the 1 because I'm 1 order of magnitude away from the 0. So I'm 1 order of magnitude away from the decimal, so therefore 10 to the 1. All right, here's another example. Again, same kind of thing I've already shown, but I want to make sure you saw this example too. This is already in scientific notation. 1.00 times 10 to the 3. These are all significant because I've said 0.00 and I've actually measured this 0 to be accurate. It's a interesting case, but sometimes when you do the measurement, you don't end up with a digit on the end that's non-zero. So sometimes you will have a 0 there, and sometimes that will be significant. And the way you represent a significant 0 in scientific notation is by displaying it. Okay, so 1.00, this is a 3 significant digit number. Hopefully you can see the difference between this number and this number, and it's because I have shaped this so that I know what is significant, right? These three are significant. That's why we use scientific notation. Now that we discussed significant figures, we'll see an application. Using two scales in this example. We have one scale, which is designed for humans and has a range from 0 to 300. This has, we can see every tick mark is 1 solid pound. So if I were to determine how many significant figures here, I could say there's 1 or maybe 2 on the 1 pound side. But this thing is really designed for higher masses. It's designed to have 3 significant figures, starting with the 100s category, right? So for our purposes, we'll be measuring small masses. Every tick mark would give us 1 significant figure, possibly 2 if you were to consider the half marks or fractional space between 2 marks. Okay, this scale is designed for letters, and you can see that it is 1 pound, correction, 0 pounds and 0.0 ounces. So that gives us a 1 decimal on the ounce side. Since there are 16 ounces in a pound, we could say that this is going to give us possibly 4 significant figures. It really depends on how much the weight is of the object. So we're going to be weighing something around 1 to 3 pounds. So I would expect that the number of significant figures that I'll get from this scale will be 3, maybe 4, as we are going to be converting to ounces, right? So you really have to be the same units to make this work out. Tips. Let's see if tips is heavy enough to be weighed without the basket. Come on, stay put. Stay put. I'm going to read that as, you put your head in the way. Stay put. Looks like 1.5, maybe 1.8 pounds. Okay, we're going to go with 1 pound and 9.2 ounces. Come here, buddy. Come here, buddy. I hope you enjoyed the video of me trying to weigh tips. So here's what we got. From the big scale, the human scale, we got 1.5 pounds. From the little scale, we got 1 pound, 9.2 ounces. We could see that the scale that was designed for something much heavier gave us a much more coarse, more average, more unrefined answer for just how big this cat was. However, the scale that was designed for smaller weights gave us a much better answer, right? Much more significant answer. Okay, so that's why we care about significant figures, because the significant figures tells us some measure of how accurate the scale was, or how accurate the measuring device was that gave us the measure. So this matters the most when we're doing scientific measurements, scientific calculations, so that we don't imply that we had a better scale when we didn't. If I did a bunch of calculations that gave me a lot of significant figures with this coarse scale, this big scale here, then it would make me believe that I had used a better scale to measure the weight of the cat, right? All right, so converting 1.5 pounds to ounces, there are 1.5 pounds. There is 16 ounces in 1 pound. Therefore, I have 24 ounces. I had two significant digits to start. I have two significant digits in the end. So now I have an answer in both ounces and pounds. And the little scale, again, 1 pound multiplied by 16 ounces divided by 1 pound. This gives me 16 ounces. I add this to this. I get 16 ounces plus 9.2 ounces gives me 25.2 ounces. We can see that from the scale that gave us three significant figures. If I wanted to look at this in pounds, 25.2 ounces multiplied by 1 divided by 16 ounces gets me 1.575 pounds. However, this gives me too many significant figures because my scale was not this accurate. It was only this accurate. So therefore, three significant figures, 1.58 pounds. Okay. All right, let's do one more example for significant figures. Let's do an example of calculating the density. So density is equal to mass divided by volume. Okay. So we know the mass of the kitten. And so let's find the volume of the kitten. All right, so I'm not going to actually measure the cat. I did some approximations, so bear with me. Let's assume that I did these measurements and this is what I come up with. I approximated the cat as a series of cubes and measured those cubes in my mind. So here, let's say that the head is 2.0 inches by 2.0 inches by 2.0 inches. Again, I want to display it this way because I would have used a scale that would have given me two significant figures. Keeping my two significant figures here. So the volume of the head would be 8.0 cubic inches. The body, I'm estimating at 6.0 inches by 2 inches by 2 inches. That ends up with 24 cubic inches. Again, I use the two digits to represent two significant figures. The tail, I'm saying 1.0 inches times 1.0 inches times 4.0 inches, or 4.0 cubic inches. And each foot, I'm saying, is 1.0 inches times 1.0 inches times 2 inches. There's 4 of them, so that's why I got 4 here. And I end up with 8.0 cubic inches. So what's the volume of the kitten? It is 24 cubic inches plus 8.0 cubic inches plus 4 cubic inches plus 8 cubic inches, or 4 cubic inches. Notice we don't have a decimal here because I have two significant figures. I'm keeping my two significant figures the entire time to indicate that that's the accuracy of my measuring devices. Okay. Density is 25.2 ounces divided by my 44 cubic inches. That's going to end up with a number of 0.57272727272727 repeating. That's what the bar means, repeating. So the 2 sevens will repeat. And that is going to have units of ounces per cubic inch, right? So ounces per cubic inch. Okay. However, this implies I have more significant figures. It implies more measurement than actually existed. So I have to round this to what was significant. I only have two significant figures. I've carried two significant figures the whole time. So I have 5.7 times 10 to the minus 1 ounces per cubic inch. So I hope that was helpful in understanding some of the nuances of significant figures. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.